Okay, so we're back. Project 4, hopefully the last project. Me, I'm Christopher, Dylan, and Noah for the next project.
Alright, so we're going to talk about the electron configuration. So right here, this is a copper electron configuration. It's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s. And then there's an example up here. This is copper. And then we go to zinc. This is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s2. And our examples up here, zinc. Then for gallium, we got 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p. And then our examples here. And then for our last one, arsenic, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p3, and then our last examples right there.
So for the band gap of our semiconductor is gallium arsenide, and that is 1.44 EV. This is our beautiful band gap image generated by AI. So do that in.
Alright, so for the P and N type doping of the two elements on their own, first up we have gallium. For the P type, because we got to have it positively charged, we have zinc, which is to the left on the periodic table. And then for N type, we're on to the right-hand side of it, because we want it more negatively charged, so we're using germanium, arsenic. For P type doping, we're going to use germanium. For N type, we'd be using selenium. It's found the same way. And then last one. And then for finding the mobilities, concentrations, and electrical conductivities of free electrons for gallium arsenide, first we have to find what the mobilities for the electrons and holes are for gallium arsenide and the electrical conductivity, which they are as given 0.85 meters squared per volt second. That's for electrons. For holes, it's 0.45 meters squared per volt second. The electrical conductivity of gallium arsenide is 1 times 10 to the negative 6 per ohm meter. And then finally, to find the concentration, we use the equation conductivity is equal to elementary charge times concentration times the mobility of the holes and the electrons. Solve that for concentration, and the overall concentration of the substance is 4.8 times 10 to the 9 per meters cubed.
Okay, finally our applications. So for electronics, our semiconductor gallium arsenide is widely used in high performance electronic devices due to its superior properties compared to silicone because of its high electron mobility. Examples of this is power amplifiers, high frequency devices, and high speed digital ICs. For LEDs and optoelectronics, the direct band gap of our semiconductor makes it an excellent material for these devices, especially LEDs. And examples of this is our infrared LEDs and semiconductor lasers. And then finally, for photovoltaics of our gallium arsenide. It's a leading material for high efficiency solar cells, especially in demanding environments. Examples of that is space solar panels, concentrator photovoltaics, and portable power. I messed that up, but it's okay. And then finally, the challenges of this is its cost. It's not very cost effective, so it's not that good. And then it's pretty toxic to the environment if you're not careful. And finally, it's pretty brittle compared to other materials you could use for the same thing.